Hi everyone, and welcome to today's GCSE physics video where we're going to be talking about sound waves and ultrasound waves. Properties of sound that you need to know is that sound is caused by the vibration of particles. Sound waves are a type of longitudinal wave, which means that sound waves cause particles to vibrate in the same direction or parallel to the direction that the sound is going in. The vibrations can travel through solids, liquids, or even gases, and the speed of the sound obviously will depend on the medium that it's traveling through. It travels fastest in air, where it's 330 meters per second. Sound needs particles to travel through, so in a vacuum where there's no particles, you cannot hear sound. The human ear is obviously the organ that is responsible for detecting sound in the human. So how exactly does our ear do this? So sound waves enter the ear canal and cause the eardrum to vibrate. And then from the eardrum, you've got loads of tiny bones in your ear, which then transmit the sound from your eardrum to the cochlea, which is that weird spiral-shaped organ. The cochlea then transmits this and changes it into electrical signals, which pass through the auditory nerve to the brain. So some terminology you need to know is that when we're talking about the frequency of a sound wave, we mean its pitch. So a higher pitch means a higher frequency, so you've got more waves. And then vice versa is true for a low pitch or low frequency. Amplitude relates to the volume of the wave. So a high amplitude wave will be louder and taller, and a low amplitude wave will be quieter and look shorter. So the human ear does have some limitations. We can't hear every single frequency of sound. So our range is 20 to 20,000 hertz. And that is more relevant when we talk about ultrasound, because the definition of an ultrasound is one that is higher frequency, so more than 20,000 hertz. The uses of ultrasound, there's many, so you can use it for antenatal scanning, for breaking down kidney stones, for cleaning jewelry, and so on. But how on earth does sound mean that we can do all of that? So ultrasound uses boundaries between different materials in order to make up a picture of what's going on. So for example, we've got a pregnant lady with a baby inside. So an ultrasound scanner looks something like that, a little bit. But if you were to zoom in, basically an ultrasound consists of a source, so that is what is sending out ultrasound waves, and a detector, which is what is receiving the reflected ultrasound. So different materials will reflect, some will absorb, and basically using the detector to pick up the signals depending on the time it's taken and so on, you can work out the depth of the boundary, and then eventually that will help you build up a picture about what's going on. So now we're going to have a small note about echo sounds, and echo sounds work very similar to ultrasounds in that it's all about the reflections to work out how deep a fish or anything or a submarine or anything is. The only difference between echo sounds is that you're actually using normal frequency waves to do the same thing you would with an echo. Moving on to seismic waves. Seismic waves are produced by earthquakes in the Earth's crust. The two main types are P waves and S waves, and the properties are P waves are longitudinal, whilst S waves are transverse. P waves are faster, S waves are slower. P waves travel through solids and liquids, but S waves only travel through solids. And I've circled all those S's because that is what can help you know the properties of S waves. So what's the point in knowing about this? So remember that S waves travel through solids only, and P waves travel through solids and liquids. Essentially, with this knowledge, we can figure out what the inside the Earth's structure is like. So S waves aren't detected on the opposite side of the Earth, which must mean there's some liquid in the center. So that's how we worked out that we have a liquid outer core and a solid mantle core, because S waves travel through solid alone. With P waves, it's a bit of a weird distribution. But basically you get these shadow zones, which is where P waves are not detected, and using this we can work out that there's actually a solid inner core. Thank you so much for watching. Let us know what you think in the comments.